Right, this is 1.1 part point 3, and the first part of it. So this will just be doing this bit 'cause it's quite a lot, this bit. I should be able to get the rest done in part 2. So here we go. So, I mean, look, I'm going to keep it nice and simple and quick because some of this is very easy, okay? So the input devices take information from outside the computer and send it inside the computer. It puts it in the computer, okay? I'm sure you already knew that, but let's go on. So, manual input devices, you've got the keyboard, a mouse, and a trackball. And if you don't know what a trackball looks like, let me get up a picture of one. Trackball, mouse. They look like that. They're often used by people who've got maybe issues with the wrist touching, the mouse, or some people like them. I personally don't, but then I do know another person that prefers them for work. Obviously, he's not for gaming or anything like that. Or maybe they use, I don't know. I very much doubt it. But yeah, sometimes used by people who have issues with joints and RSI, repetitive. Is it stress or strain? I don't know. I'm going to put stress, that's strain, injury, because I think it's called both. Which is a problem where you basically use a joint too much, or you get a lot of issues with the mouse where your wrist constantly make contact with the table and you can press down on nerves. And you can get something called carpal tunnel syndrome, which is like a burning nerve damage. And a trackball helps with that because it lifts your wrist, the actual wrist, off of contact with the table. Whereas with a mouse, you're sort of placing your wrist down onto the table before you touch the mouse, and that pressing down the nerves can cause damage over a long time. So obviously you've got touch screen inputs and you've got interactive whiteboards, okay, used a lot in schools. One thing you should make note of, because I could see a question coming up about this and you might just write what it is, but just remember with an interactive whiteboard that you can save the annotations you do on the screen for later use. So you've got to try and remember that possibly could be a thing that comes up in the exam, possibly this as well, for the other thing I said about why people might use a trackball device. So just try to remember those two things, because yes, it's an easy topic, but just try to remember those little extra things that they might want you to say. So then you've got scanning devices, and these scan things, obviously. So you've got a barcode reader where a light is shone onto the barcode image and the reflection is captured. The light will only bounce off the white parts, so the system can work out where the data is. White is 1, black is 0. The other bit is this that you need to know, because obviously that was quite obvious. I'm sure you worked that out. They have a check bit at the end. So here, I'm not quite sure exactly how it'll be different on different types of barcode. But what a check bit does, and I'm just going to get up Paint, is imagine if we had 4 numbers that were being read. 4, 6, 3, 2. And you wanted to work out if that was correct, that was a valid product. So have I read it correctly? What you can do is you can add a check bit. So let's add these all up. 4 plus 6 is 10. 3 and 2 is 5. So we've got 15. We could just take the last digit of that, 5. Now, if we read that in, the computer can read those 5 numbers, add those up, look at the rightmost digit, the least significant digit, and if it doesn't match up here, then the barcode reader has read it wrong, or it's an invalid barcode. But hopefully you wouldn't make an invalid barcode. So that's what check digit or check bit is. They add a digit. They can do it in other ways. You could multiply them together and then take the last digit. You could have 2 digits. You could actually have 2 digits. So you could have 15. And then obviously if there's an error, if you accidentally read that as a 4, then you would know this is wrong because it doesn't add up to the last 2 digits there. So that's what a check bit is here. Okay, there are different types of barcode. I've got to be honest, I'm not quite sure how much you need to know about barcodes, so I just thought I'd give you the basics. There are very different ones. Some of them only allow numbers, some of them allow numbers and letters, and obviously you've got now the 2D barcode, which is a QR code, often used in advertising. So you might need to know this. It was mentioned a bit. Just make sure that you know they're sort of using advertising as well as other things, shops, magazines. Feel free to scan that one. It's a little extra page I've made on some topics you might want to know about. So have a little look at that page for some extra details. But yes, that's QR codes, really, and barcodes, not the most difficult topic. So obviously another scanning device is a photo scanner or a document scanner. This is the first ever scan by Russell Kirch in 1957. And basically they work by, they shine a light onto the image and then read how much light bounces back off, really. It's not rocket science. And then they turn that into a digital image. For the different colours, they obviously shine a white light. and they have a red, green, and blue sensor. So it measures the red, green, and blue amount, and you can push that back together to get an image. They are still used quite a lot for legal documents or to scan other people's photos. A fax machine kind of has one of these built in, and apparently fax is still used for legal in some ways. A fax machine, in case you didn't know, it takes a document, scans it into the device, and then it will send it over the telephone system to another fax machine, which will print it out. So a fax machine is kind of like a scanner and a printer and a phone, and they are apparently still used in some legal ways because of tradition and laws and other things. Right, other scanning devices. You've got facial recognition, and what it does, it basically compares data recorded from a scan to one of a previous by measuring the facial features. Just to be clear, AI has made this far more advanced than the simple method now that I'm talking about. It does much more clever things about tone, shade, depth. You've got different types of cameras now that can record the X, Y, and Z position. Whereas obviously here we've only got like the X and the Y. And we don't have any depth. Maybe you can infer depth by some clever way. So this is a sort of simplified version of modern face detection. But basically it picks points on the face and then measures distances between them and then compares that ratio with other ones of that image. I won't bother reading these out because you can read. But yeah, so that's basically how it works. Right, so 3D scanning. This is something you probably haven't thought about or heard about or bothered to think about. But a 3D scanner will try and take a scan of an object and turn it into a 3D model on a computer. You might have seen it in films. It always looks really cool in the films. But, it's a bit over-realistic. So you can see here, it's not the best picture. If I maybe enlarge it a bit, you can see that. That's a finger sort of shushing. And you can see that this has taken a scan. It's rotated the object, obviously. That's why it's on this rotating thing. And it's scanned it in. They mostly work using something called tomography, okay, which is basically where they take a scan of slices of the object, like the thickness, all the way around it, and then they place it, they sort of slice it back together on top. So if you can imagine that I've 3D scan this, the slices will be really thin, way thinner than this is denoting. They'd be like millimeters, maybe less. I don't know, it depends on the quality of the scanner. So they take a scan like of that, and then they go up 1 millimeter and scan that, and then that, and then that, and then that, and they keep going up, scanning around it until they get an image. And basically they end up with a load of slices all the way. Just edit my spelling error there. Yeah, all the way from the bottom. So they end up with that, and then they can rebuild that up to make the 3D model or image. Another scanning device that does a lot of tomography is a MRI scanner, magnetic resonance imaging. I've had one of these myself because I had headaches a lot, and it's quite interesting to have. And basically, from what I gather, it magnetizes all the body so that all of the cells line up in some sort of northern way, and measures how long it takes them to return to their previous sort of pointing. I don't quite know. You have to look it up. It's obviously very complicated. What a complicated machine it is. But basically, that's the same. It scans in slices. It goes across your body, taking a sliced image, and then of course they can re-put it back together to rebuild a 3D version of that. Obviously magnetic resonance imaging can be used in lots of things, but it's mostly used in medical as far as I know. Possibly could be used in some sort of maybe, I don't know actually, I don't know, maybe some sort of scanning of things coming in from other countries. I don't know whether they do that, but then magnetic probably isn't good, because obviously you have to be very careful that you don't have any metal in you when you go in there, because obviously magnetic, it's going to stick to it. So how do things actually scan stuff? So we just covered, the input bit of it. So how does it actually scan stuff in? Well, yeah, I'll show you. So it uses things called sensors. A sensor, just a normal one, just to be clear, because you do get sensors anyway, it's just a word, is an analog device used to measure something. Think of an old school thermometer, or like just one of these old mercury ones that look like this. This is a sensor, but it's not digital, it's obviously analog. Okay, so there you go, it's obviously an old school sensor. Speedometer in a car. Nowadays, obviously, we've got electronic sensors, okay? Sometimes referred to as input transducers. So I'll highlight that. And they measure real-world quantities, right? So they convert them into electrical signals. Sensors often constantly send data to a computer via an interface box, and you must know that word interface box. This is the bit I think you need to listen to the most. Okay, so it uses an interface box. So the sensors go to the interface box, which an analog to digital converter turns these analog signals into digital. Because they're still electronic, they're electrical, but they'll still be analog. Think of a microphone. It comes in as positive, negative waves, and that needs to be converted to digital signals through some ADC. And we know with sound, it takes a sample of it, and that'll probably be how it does it for most of the others. It will take a sample of data at certain times a second, and then turn it into a signal. Very similar to sound, very similar thing. And that's called an analog to digital converter. It could be inside the sound card. In sound, it could be a special device for other things, okay? So there's lots of types of sensors. I'm not going to go through them all. Obviously, temperature, use an oven, microphone, light. Light sensor can be, turn on street lights when it gets dark. Infrared's used in remote controls. Also used in security systems because, and how it works in security systems, and I will mention this because it's a common question. Infrared sort of detects heat because heat comes off like that. And it takes a picture of the scene and then another picture very quickly, and it compares the pictures. And if there's been a lot of change in picture, then someone's moving around in the room, or heat is, and people give off heat. So yeah, that's how those movement sensors work. Some of them work a bit different to others, but basically that's it. They take a picture, take another picture. If there's a lot of change in the picture, then there's movement, and then you need to set the alarm off. You've got pressure sensors, gas sensors, humidity is how much water's in the air, and a gyroscopic sensor on your phone checks for which way up things are being held, or is which angle are they being held at, and you can use it for gaming or stabilization in robots to work out when they're falling over and tilting or whatever. Any self-balancing system would use a gyroscopic sensor. Yep, so I'm not going to go through all that. Okay, so now there are two types of system we need to look at: monitoring and control. Monitoring just take readings of the system. So for example, imagine if I set up a system to record the temperature outside for a year every hour. That's a monitoring system. It doesn't do anything, it just records it, because I might want to make a graph of that later. A control system will take some input from the sensors and then do something with it, like alter something. So for example, a central heating. A central heating will turn off when the temperature reaches a certain thing. Okay, that's a version of control. Okay, not too complicated. Detection. These detect when something happens. A burglar alarm system is a good example of this. A pressure sensor on the floor, magnetic sensor on the window. So you've got a magnetic sensor. It basically knows when it's near a magnet, and then you pull as the window gets open. It's further away from the magnet, and then the sensor detects that the magnet's gone, and alarm goes off. So that's a detection system. So you've got the monitoring, control, and the detection system is really a part of a control system, really. But yeah. So anyway, this is a question you could get in the exam, like that. That could be a question, right? An oven is turned on, heating has started, and set to 180 degrees. Explain the control process. So here is what you would have to write out: that the temperature sensor reads the temperature. Let's get rid of the sends. And sends the data to the processor through an interface box. Okay, remember the interface box. An ADC, analog digital converter, inside converts the analog data into binary form. The system checks if the temperature is greater than or equal to 180 degrees. If it's true, the system will turn off the heating element. If it's false, the system will turn it on. It's important that you say the false. This confuses some students because remember, this is going to go, by the way, and then the process repeats. The reason we've got to do this is otherwise an oven needs to be continuously turned on and off to keep the temperature. It doesn't just go up to 180 and turn off and then drops down to 160 and your food doesn't cook properly. If the heating drops back below, now it may do a thing, I don't quite know how they work. They might do it 185 degrees or something like that. Or do a thing where it turns on up to 180, but there'll be some sort of balance. Because otherwise what could happen is it could go off on, off on, off on. So it might be it has 2 degrees leeway or something either way. So once it gets within 2 degrees, 178 or something, it turns back on. I don't know quite how each oven works or what the legal requirements are to keep food cooked. I don't know. But anyway, that's a sort of example of a question that you could get in the exam. Okay, so we now are going to look at the output devices. That takes data from inside the computer and sends it in some form or another out of the computer. It could be printed text, a photo, sound, a video, a 3D model, like in the 3D printers, whatever. Basically, the opposite of an input device. So we're going to look at the printers first. So an inkjet, which is a very common form of printer, especially in the home or small office, essentially runs across the page and sort of shoots ink at the page as it goes across. The costs vary from being very cheap to very photorealistic. They are cheap to buy generally, but the ink can be very expensive with inkjets. That's how they get you. Sometimes the printer is actually sold at a loss, but the ink is where they get you back. And they do a cheeky thing sometimes where if, let's say, you've got like no red ink, but you've got green and blue and black, and your image only uses black and green, it won't print. It will say, no, you need to replace the red. So it is really annoying. I've had many of them. I don't like them at home. I don't think they're very good if you don't use them very often because it's ink and therefore it's a liquid. It doesn't dry out inside the actual cartridge, but obviously some of the ink is in the sort of system in the nozzle that gets fired out and it can get blocked. So if you don't use the inkjet very much, what happens is when you go to print, the nozzle that obviously fires the ink out is blocked with the dry ink from before. You've got this cleaning process you have to go through. But in the end, honestly, I found them really annoying. But if you do want to do a lot of colour printing at home, then they are the best, really, because colour LaserJet, which is the only other real option, is quite expensive, although they are getting cheaper. I have a LaserJet printer, black and white at home. It's brilliant. I don't really print much colour out. Obviously, I work in a school. I can print colour out on a LaserJet colour printer. We have really good printers at the school. So I wouldn't really, and I don't really print any pictures out anyway. But the point is, LaserJet doesn't have that problem of the ink drying out because it's powder. So it's already dry. But yeah, that can be a problem. And just to be clear, it's the ink drying in the nozzle, not necessarily drying in the cartridge, or that could happen because they're kind of airtight. But they can dry out in the nozzle that fires it out, and then you have to sort of clean it, basically. It's got its own process, but I found it never really worked brilliantly. But LaserJet is a very common form of printer in the office. They are getting cheaper for home. I only paid about 75 quid for mine, and I've got to be honest, it's pretty much perfect. They print very quickly, much quicker than inkjets. Yeah, they're fast and reliable, and I would say they're the best. They produce the best quality print of all because they're very accurate. There's a common misconception with LaserJets that they burn the paper. They don't laser any paper. What they have is a drum inside it, like a roll. I think of a rolling pin. And that gets a static charge, right? And it gets a negative. It has a positive charge applied to it, right? Then, where the laser shines onto it, that becomes negatively charged. So as the roller spins, it rolls over the ink, which is a powder, okay? And that then flies onto the negatively charged. It gets attracted to the negatively charged drum, and then that is rolled onto the paper, okay? So it doesn't actually burn the paper at all. It lasers the drum. The drum then gets negatively charged where it lasers, and then the ink jumps to that and then gets rolled out onto the paper, slightly heated, I think, as well, to sort of not melt it, but sort of like, and then it rolls it out onto the paper. Yeah, quite good. The ones around the school we use are LaserJets. They're very fast. Most offices use them, and the ink is called toner. But remember, it's not ink, it's dry powder. So, dot matrix printers. I mean, I don't know if you need to know about these, but might as well do it. They're a very old style printer where dots are punched. So basically, imagine like you've got like, as it goes across, it just dot the page, if you can think about it. It's a very strange, in the modern era, it's not used at all. They're very noisy. They're like, they produce a very poor quality print, but they are super robust. So they can work in bad conditions, but they are pretty pricey because, maybe because they're out of date more than anything else. I can't imagine where you would use one in the modern era, but maybe there's a situation because of the fact they're so robust. They might work better in some conditions, like wet conditions or something like that. I don't know. Very strange. So that's printers for you. So now we're going to look at 3D printers. They're used to print a real solid model of an object. They use the ink is sort of acrylic or plastic, but there's different types of ink you can get. And it's on a reel like this. Can be a little pricey, the models. This isn't cheap. But it's amazing technology. I thought about buying one, but of course I have no use for one, so it's just for pointlessness. But they're not as expensive as they used to be. They used to be really expensive, but now you can get a good one for say £300-400. Although I'm not an expert on them, I've never actually owned one. I've used one obviously to mess around with. But yeah, so here are some uses of a 3D printer, because I can see this being a big question. So obviously in medicine, you could produce prosthetic limbs. You could therefore make them more accurate. You could like have more few goes at it. You could do a bespoke one. You could have some sort of system online where you scan your feet and then it, you know, your stump of where your foot should be or whatever, and then it produces the foot for you. You could scan your other foot, for example, as a template to what your foot should look like. So you could see how it could be a lot more bespoke for that. Obviously, you could build parts. I'm not talking about the electronic parts, but casings for things, for machines, old cars, anything that's out of date. Let's say you've got an oven and the knob's broken, but they don't make it anymore. You could print it out, and it would be useful, or a clip or something. And as they get more and more advanced, you know, this could be a definite thing for the future. Prototyping design is obviously one of the key things they use for. So if you're designing a car, you can literally print it out and have a look at it. It's good to look at things in real life. Models for tabletop gaming, any game models or pieces can be done on there. You can obviously design your own ones and print them out. You know, they're quite good for any engineers. They want to design some sort of piece they need to hold their project together as well. So I should have put on there really for engineers in their projects. Okay, but I spelled there horrifically wrong. The dangers of 3D printing are obvious, really. That you could print out a weapon, a knife, but they have 3D printed a gun. So that's not good. It obviously needed a few other bits, but not a lot of that stuff was hard to come by. And maybe soon you won't need any of that. Maybe you'll be able to print some metal parts out. Maybe you can now. I haven't really looked at 3D printers for a long time. So, but yeah, so you can obviously see the dangers of 3D printing, but there you go. So we're going to go on to some of the things that, well, also output devices. So output can be movement. Sorry. So an actuator is a posh word for some sort of motor or movement device. You really sort of get two types, but there might be more. I'm just going to look at these two now because you don't think you need to go deep into this. But yeah, they can be used to move things. So a rotary one could open a valve. You see there, it's got a disc. A valve could be in a pipe to stop, or like let water out, don't let water out. So inside the pipe, there's this disc, and the valve was what it's called. The actuator would turn the valve, and then it would be shut, and then it opens the valve to let water through or gas through. And you get a lot of these in car engines, because in car engines you've got to adjust like oxygen level, and you can adjust it by sort of not letting as much air in, you know. So that's a rotary one, but they could obviously be used for many other places. Anyway, you want rotary movement, a door opening maybe. And then linear is obviously forward and backward, side to side movement. But yeah, it's often when we look at robotics and how they're getting them to stay up straight, is that we actually haven't got anything. Well, we probably some top scientists doing it now, but the human muscle is so good compared to like what we have in electronic versions, because the human muscle can sort of contract, move in many directions. It's 3D, whereas we struggle to really do a sort of 3D movement device. I'm sure the top scientists are out there making one now, but yeah, rotary and linear is easy, but that's not very useful for robots. And of course, you can make linear do rotary by putting it onto a cog or whatever, and you can make rotary do linear by putting it onto some sort of mechanical thing to make them happen. So even a linear actuator can do rotary movement, because if you imagine that had like cogs on it, a cog here, and as I push forward, the cog turns the cog here, the pieces turn the cog, then you can see you can turn them back and forth. So so yeah, that's basically actuators, very useful in life. Right, well, obviously I'm going to just do this one very quickly because it's easy. So speakers or headphones or anything that does sound. Basically, a speaker simply turns digital data back into analog using a DAC, the opposite from before, a digital to analog converter. So it turns ones and zeros back into analog. Often it requires amplification before being played, but I'm not going to talk about this too long because that's what a speaker does, and you know that probably already. So there you go. Just remember that it uses a DAC. Obviously, it's the opposite of an ADC from a microphone. Now we're going to look at monitors, and let's have a look at them. So this is LCD or LED monitors. We're going to get to OLED, which is the more modern ones, and it's also QLED, but they're quite expensive. Pardon me. But anyway, so how it works is you've got an LCD monitor. Okay, so liquid crystals. These are both liquid crystal displays. Okay, they're just lit differently. Okay. So an LED monitor is an LCD, right? Just to be clear, it's just a different type of OLED, but an OLED is not the same. Now, that seems weird, but let's get to that. So a liquid crystal display, basically what happens is, if you can think of, you've got loads of like filters that can block. Each pixel is made up out of 3 filters, red, green and blue. So let's just think of one filter. Imagine you've got a torch and you've got filters that block the red, green and blue, or allow red, green and blue light through. If they're all letting it through, it'll be white. If the blue and green ones are not letting it through, it'll be red. And that's basically what liquid crystal display does. You can send a signal to the filters and they'll either let a certain amount of light through or not. And there's a red one, a green one, a blue one, and that makes up the image. Now, because they're filters, they're not lights themselves. They're literally like that red transparent thing I'm talking about that you put over a torch. It's just that it can change how see-through it is and how not see-through it is. So they don't light anything themselves. They have to be backlit. So they've got lights behind them shining through these filters. And there are 2 ways of doing that, main ways. So one using a cold cathode fluorescent lamp, which is a bit like those big long bar lights that you see, like maybe sometimes flickering. Like, I don't know if the schools still have them, but often like in big buildings when you want to light a big area, they can make them smaller. This is an image of one out of a monitor, and it's not very thick. I suppose it's about the size of a breadstick kind of thickness, maybe a bit bigger. I can't think of anything. Maybe like a small glue stick. But they're not very good for the environment because they have gas inside them, and this gas is not good. So it's got fluorescent gas inside it, and so they're quite annoying for the environment. They don't produce as good at picture, and they do take time to sort of glow up. They've got an older technology now, but you probably find some still around. So the more common one is the LED light emitting diode. So it's the same system as that. It's got these filters, but the way we backlight it is with a series of LEDs, which are light emitting diodes. They're much better for the environment. They're smaller, which allows the monitor to be bigger. They can be placed better around, so you get more smooth lighting. You could place like loads of them. We could do more than that. This is one picture I found. You do get more than that on a lot of them. But here's the thing about them is they're lower power, much better for the environment, more reliable, and they just produce a better picture really, and they light up quicker. So just generally better. So the last of the monitor types we're going to look at is the organic light emitting diode. It's basically a diode which has got organic material inside it that when responded to will send out light. If you want to look more into that, you're welcome to. You don't need to know it on this course, and it can get a bit sciencey. So it's really interesting to read, but obviously not too long for this video. So they literally generate the light. So they do not need to be backlit. Okay, so with the LEDs, they're just doing sort of like light, and then filters are causing the red, green and blue. But with these, they literally produce the colour, the red light themselves. They use very low power, produce very little heat. Plastic screens make them really easy to bend, etc. So they're good for like mobile phones, etc. And they're good when small screens. And they're the brightest and best picture, and they're eco-friendly. They're just the best, but obviously they're a bit more expensive at the moment than the others. Obviously they'll come down to the price of the others. I don't think you can get an OLED screen that isn't 4K, for example. Maybe you can. I could Google it. Let me just quickly Google, is it worth bothering? But anyway, OLEDs, 1080p. Let's have a look. Oh, you can get some, but they do normally start at 4K. It looks like they, 4K resolution. So, that's basically it. And, monitors. That's monitors for you. You've got one last thing to cover. And that is projectors. I'm not going to talk too long about a projector because it's kind of obvious what it is. So a projector projects an image onto a surface. They're often used in work or schools, although the lamps themselves, the bulbs inside there go. And they actually can be more expensive than the projector itself. You might go online and have a look. You think, oh, that's only 300 quid. And I think this is 300 quid. But you might find that when the bulb goes, you've basically got to pay 300 quid again. They can be quite expensive. They sort of sell these a bit like the printers before the ink is more than the printer for inkjets. This is the bulb is more than the whole thing. So that's basically it. Projectors. That's all the monitors. Just one last thing to cover. Right, and on to the last thing, which is an RFID, radio frequency ID system. It's what you tap with your car when you buy stuff. It is an input and an output device. It uses something which is in other things, not just an RFID, called a transponder. I think of it, and it probably is where the mashup of the words come from, transmitting responder. So what happens with the transponder is it will only send a signal back when it receives a signal. Okay, you do get some tracking devices that use this, because obviously you can track, if a tracking device was constantly sending out where you were, then someone could detect that signal and know they're being tracked. But a transponder can be used to track someone, because you could then send a signal to a transponder to say, where are you? It then sends back where you are, and only then would it be detectable by the people. So that's another use of transponders. So a passive version of the RFID, this is back to just RFID now. The signal sent to it actually powers the device. Okay, so the because obviously there's power in that signal, and it's enough to actually power the device to send the signal back. There's no battery in the passive version, so your tap card, all the other stuff, there's no battery in there. So they obviously, because there's no battery and the signal powers it, they've got a short range. Okay, and they could replace barcodes and allow auto scanning of products. Amazon's done this. You just walk out the store and you pays for the goods. Obviously we use it in banking and other things, but it has a relatively short range. Okay, there is an active tag version which actually has a battery in it, and it can go much further, over 200 meters. But yeah, so that's it. That's this whole section done. That was a long video. It felt long doing it. So yeah, if you have any questions, that's 1.1.2.1 part 1, because I was going to do all 3 parts, but this video is far too long, so I'm stopping it here.